All right, so today what we're going to see is we're going to talk about the quality of a system of equations or the conditions of systems of equations, which we can represent through matrices. And then we're going to go through a civil engineering example of how we can use matrices to solve civil engineering problems. So the first thing we're going to be talking about is the condition of a system. And when we're talking about a condition of a system, it's either well-conditioned or ill-conditioned. Basically, why that matters is because if we set up a well-conditioned system, then any small changes to the system won't make large changes to the output. When we have an ill-conditioned system, the opposite is true. So we have small changes to the system make large changes to the output, and that can be problematic, especially when we're dealing with problems where things may change slightly, or we might have we might have places where we might make small errors, and if those small errors make massive changes to the outcome, then the system isn't a good system. So it's not a good way to do tests and check and make analysis. So what I basically said is what those two paragraphs above were. What we are going to look at, I'll show you what that kind of means graphically, is that if we look at these two equations, which you can write in our matrix form if we wanted to, right? A11, A12, A21, A22, X1, X2 equals B1, B2, right? So that's our matrix form. That's why it's a system of equations, and that's how we can use that to solve that. What this would look like graphically, though, is they're both linear equations, and what we would have here is we could have two separate scenarios, right? So I'm going to draw them out here. If we label this one as well-conditioned, and this one would be ill-conditioned, what they'd look like graphically is if our matrix was set up properly and everything, this one would look something like this, and this one would look something like this, right? So any small changes to these lines would still hone in on kind of this answer here, right, as our solution to the matrix. This one, any small changes could drastically change where the lines cross, and it could end up changing the solution. So that's basically what it looks like graphically. All you need to know is that a well-conditioned system means that small changes make small changes in the input make small changes in the output, and an ill-conditioned system means the opposite. How we to determine whether a condition is well-conditioned or ill-conditioned is using the determinant. So a couple of conditions. Basically, we have these three conditions where it says the determinant of the matrix is much smaller than any of the maximum elements in the coefficient matrix or A matrix. Or if the value of the inverse of the A matrix is much greater, any of the values in the inverse is much greater than the solutions for X, or if any of the elements in the diagonal are larger than any of the other elements, significantly larger than any of the other elements in the matrix, then these are all conditions for an ill-conditioned set of equations or ill-conditioned system. Anything else is basically a well-conditioned system or better, like it's better than ill-conditioned. So what we're going to do is we're going to actually go through an example of a system of a matrices, and I'm actually going to use Excel because we're going to start to use Excel to solve for our matrices instead of just doing everything by hand. And I'll go through and remind you guys how to use Excel for matrices, and then I'll show you after this another example of an actual civil engineering problem, and we're going to use Excel again. So if we have a matrix that looks like this, that's the first part. Just writing out the original matrix here. These numbers don't mean anything. They're just plucked from an example. And I want to show you what it's going to look like here. It's got x1, x2, x3, and x4. And then we've got our solutions, which are going to be Now you can see based on the conditions that we have above, this is an ill-conditioned system, right? We're already meeting that the elements in the diagonal are larger than any of the other elements, right? So our 20,514 is much bigger than 4. It's also much bigger than 14 and 54, even 224, right? So it's much, much bigger. It's orders of magnitude bigger. So therefore, this is already looking like an ill-conditioned system. So what I've done is I've gone ahead and I put it into Excel. And in order to solve this, well, we can do two things. The first thing I'm going to do is calculate the determinant. So when using Excel, we can either type in the formula if we know it. So in this case, it's mdeterm. And we select our array, and then we hit enter, and we get out that the determinant is 144. So I'm going to go back and write that. All right, so we've calculated the determinant using Excel. It's relatively straightforward. The determinant of the matrix is much, much less than the maximum elements, right? So 144 is significantly less than 20,514. So therefore, again, we're seeing that this is an ill-conditioned system. So what we're going to do, I'm going to solve this. And in order to solve this, I'm going to find the inverse, right? So I'm just going to label it A to the -1. And in Excel, when you're using matrices, what you have to do is you have to select, the inverse is going to be the same size matrix. So I'm going to have a 4 by 4. So I'm going to select 4, and I can go up to my function here, and I can type in what I want, but it's already at the top because I've gone and done this, and I can select M inverse. Tells me the array that I need to select. So what I do is I select all these, and then instead of hitting OK, like you normally would, you have to hit Control-Shift-Enter. If you don't hit Control-Shift-Enter, it doesn't create a matrix. It just gives you the one spot that you were highlighting. So that's a really key thing to remember for Excel and matrices, is that you have to hit Control-Shift-Enter every time you want to solve for any sort of matrix function using a matrix. So what I've done here is I've just copied my Y matrix, and I'm going to multiply it by the inverse. I'm multiplying both sides. So A multiplied by the inverse is 1, is the identity matrix, and then the Y times the inverse will give us our X values. So this will be X1 through X4, and all I'm going to do again, select the matrix that I want, equals M mults, which is multiplying two matrices, and all I have to do is select the first one, select the second one, and then again, Control-Shift-Enter. And that gives me my values. Now, if I change those to number, and I get rid of a whole bunch of decimal points, basically the matrix, the answer to the matrix is 1, 0, 0, 0, 1, or 0, 0, 0. So what I've just done here is I've solved. We go back to the notes and we say that the values of the inverse are much, much greater than the solutions of X. We can go back and look at it and say that we got 681 there, and a negative 708. So 1 and 0 are significantly less than those numbers. Therefore, we really do have an ill-conditioned system. So what we got is, we're going to answer x1, x2, x3, x4 is, in this case, is equal to 1, 0, 0, 0. Now, I want to show what happens when we do something here. So if I go ahead into my Excel spreadsheet and I change this one number to 20,515, so I change it by 1, the change for the solution is drastically different, right? So that's what I mean by an ill-conditioned system. So if we were talking about, well, we're going to go through an example where I do a civil engineering example of a truss. If we were to go through that, then the answers we're getting here are drastically different because I changed the 20,514 to 20,515. So that means our margin for error is significantly higher. So anytime we have a truncation error, anytime we have a rounding error, anything like that, we're going to have a very large difference in the solution. So that's not a good way to set it up. So that's pretty much all I wanted to go through for the idea of well-conditioned or ill-conditioned matrices. Now I'm going to go through a civil engineering application. So one of the applications that we can use for our purposes, our matrices for our solutions, is we can use it to solve for a truss. The nice part about a truss is it only loads axially, right? So we're only dealing with one force for each of these, right? So P1 is equal to P1, either in tension or compression. And so we're only using one force for each member of the truss. It would get more complicated if we were talking about frames, because now we can introduce a moment, we can introduce a shear, and it gets more complicated. But what we're going to do here is we're just going to do a very simple truss, and I'm going to show you how we use matrices to set up for those equations. So the first thing that we have to do is we're going to use the method of sections to solve for each joint. And I'm going to leave everything in terms of its variables for now. So there's a lot of more work up front in this question to do, because it's such a simple question, to do the matrix math. But this is also the same way that computers solve for these things. So even as it gets more and more complicated, the process doesn't change. It's just the number of variables and such. And for more complicated trusses, it's a lot easier to solve for more complicated truss systems, and it solves for the entire thing right away when we're dealing with more complicated systems. Sorry, I keep saying more complicated systems, but that's kind of what it is. So I'll show you. It's more upfront work, but it'll give you a little bit of it'll give you the answer quicker with the use of computers as well, once we realize how to set up our matrix. And then we can make quick changes and modifications to different values. I can adjust the applied load not only in direction but in magnitude, and I can get the answer to this whole solved truss very quickly. So that's 4 meters, and this is 3 meters in height. I'm drawing my free body diagram, and I'm going to call this theta and this alpha. So theta is equal to tan -1 of 3 over 4, which is equal to 36.87 degrees. And then we've got alpha, which is equal to tan -1, the arctan of 3, and that's going to be equal to 71.56 degrees. Just having a look at them, yeah, that makes sense. The angles make sense compared to how it's drawn. And all I've got listed here is my reaction forces, and then my RBY and my RBX, and then my applied force. So what we're going to do is we're going to use the method of joints. What we can do, this is the long way of doing it. There is another way of doing it. We'll go over that in another class. But I'm going to go through this simple example to show how we set up the matrix and then how we use them to solve for them. So what we're going to do is we got joint A, and I've got my FAC. Oh, I forgot to draw the ACB. So I got my FAC, and I got my FAB, and I've got my RAY, right? So this is theta, which is 31.6. So what I've got here, I'm just going to do the sum of the forces in the x. So that's positive. I'm going to keep this positive and negative for the entire truss. So we have to, if we decide that right is positive and up is positive, I'm going to have to keep that for the entire truss, because that's how I'm creating this matrix. So what I'm going to get is that I get FAB plus FAC times cosine of theta, which is 36.87. which is equal to 0, right? So those are the only two forces in there. And then I'm going to do the sum of the forces in the y equals 0. And I'm going to say up is positive. So I've got RAY plus FAC times sine of 36.87 is equal to 0. So I'm going to label these as equation 1 and equation 2. And I'm just going to continue along. So joint, I do C next, I think. C is going to look something like this. So this is F BC and FAC, right? Equal and opposite. And now this becomes my 36.87 degrees. And this becomes my 71.56 degrees, and that's from trig. And I've also got my 250 kilonewton force down. So I'm going to do the same thing. So the sum of the forces in the x equals 0. So I've got negative FAC times cosine of 36.87. And then I've got plus FBC times cosine of 71.56. So that's the x component of each of those. And then I've got the sum of the forces in the y equals 0. Up is positive. And I'm going to have negative FAC times the sine of 36.87 minus 250 kilonewtons minus FBC times the sine of 71.56 equals 0. I'm going to rearrange that one. So I'm going to say that negative FAC times the sine of 36.87 minus FBC times the sine of 71.87, or 56, sorry. 56 is equal to 250. So now I'm going to call this equation 3, and this is my equation 4. So this is all I'm doing is building up my system of equations. And finally, we're going to do joint B. I don't know if I should do it here, if I have room down below. Just give me a sec. No, I'm going to do it right there. So joint B, what I'm going to have is my FBC, right? And I've assumed they're all in tension. I'm just going to leave them all in tension because that'll matter after. FAC. Oh, that's a really bad arrow. So yeah, I forgot to mention that I'm leaving them all in tension. And this is RBY and RBX. That's an important distinction that I should have spent a little bit more time on. But so not only when I was back at A and I said that this has to be my sign convention for the entire system, I'm also assuming that all the members are in tension. So when I get a positive answer, then it means it's in tension. If I get a negative answer, it means it's in compression. So I'm going to go over that at the end, but I need to make sure that you guys understand that as we're going. So f at x equals 0. That's positive. And then I'm going to just keep doing the same thing. So negative FAC, or FAB, sorry. Negative FAB minus FBC times cosine 71.56 minus RBX equals 0. So that's my equation 5. And then the sum of the forces in the y equals 0. And that's going to give me FBC times sine of 71.56 plus RBY is equal to 0. All right, so that's my equation 6. So if I'm going to write down, actually, just to keep everything straight here. First of all, I'm just going to say that the cosine of 36.86 is equal to 0, or it's approximately equal to 0.8. It would be equal to 0.8. But again, I did some truncation errors. So that's approximately equal to 0.6. And then the cosine of 71.56 is equal to 0.316. And the cosine of the sine of 71.56 is equal to 0.949. So I just wrote those down. Now what I want to do is I want to construct my matrix. So there's a couple ways you can do this. One of the ways I'm going to show you is how I kind of keep everything straight. So what I'm going to do first is I'm going to construct my X matrix. 1, 2, 3, 4, 5, 6 equations. So I'm going to have 6 in my X matrix. And in that, I'm just going to start listing off the unknowns. So I have FAB. It doesn't matter what order you put them in here, but this is going to determine the order for the rest of your matrices. So FAC. So I've got AB, BC, AC, RAY, RB, how did I write it? X here, RBY. Now, so that's my X matrix. I'm going to do that one first. So now I know that I've got my 6 by 1 matrix. I know that I have 6 equations, so I know I'm going to have to deal with 6 equations and 6 unknowns. So this is going to be a 6 by 6 matrix. I'm just going to try to make this big enough here to deal with something, or to deal with the entire system. So again, once we've decided how many unknowns we had, we create that X matrix. We've got to build the other matrix that we're going to multiply it by and then equate it to yet another matrix. So what we do is we know this is a 6 by 1. We know we have to multiply it by these two numbers have to be the same. So it's got to be something by 6. So 6 columns, right? And we know that we've got an equation, or 6 equations. So what we're just going to do is that's equation 1, 2, 3, 4, 5, 6. So it's going to be a 6 by 6 matrix. So all we're going to do is we're going to go back to our equations, equation 1 through 6, and write in the values that correspond to each of the unknowns. So for equation 1, we have FAB plus FAC times cosine 3.86 equals 0. So equation 1, I've got FAB, right, which is 1, times plus FAC, FAC times cosine of 0.36, or 36.8. So I don't have an FA and FBC in there. I have an FAC, which is going to be equal to cosine of 36.86. And then I don't have any of the RAYs, RBXs, or RBYs. So I'm going to have 0, 0, 0. And that equation is going to be equal to 0. All right, so we just continue this and do it through the other equations and making sure that we keep the signs and the values correctly. So equation 2 is RAY plus FAC sine of 36.86. So I've got an RAY, which is the fourth one. So I've got an RAY plus FAC times the sine, which is 0.6. And then the rest are zeros, right? Because I don't have any more of the variables in there. And that one also equals 0. So I can do the same thing for all the values. And what I'm going to get is something that looks like this. Negative 0.8, 0, 0, 0. So equation 3, according to what I just wrote down, is 0.316 times FBC minus 0.8 times FAC, and that's going to equal 0. So we go up and we check, and we've got equation 3, FAC times minus point. That's equation 3. What did I have here? Oh, minus 0.8. Yep. And then FBC times 0.316. And so all I'm doing is just filling these out from the equations. The next one is going to look like this. And I list zeros. So I've got another FBC and another FAC, and then the rest are zeros. But this time, this one's going to equal 250, right? Because if I go up to equation 4 and I talk about my external forces, then I've got it equaling 250. So I'm just going to finish up the matrix here before, and I'm just going, all I'm going to do is methodically go through my formulas that I've created and make sure that they correspond to the variables in the X matrix. 0.949, 0, 0, 0, 1, and then these are both equal to 0. So now I've set up a system of equations in order to solve for that truss. So if I go into Excel and I put them into Excel, I'll call this my A matrix, and it's going to be, oh, I think I already got that set up somewhere. I do. Okay. Whoops. No, I don't. Okay. All right. My A matrix is going to be a 6 by 6 matrix. It's going to be 1, So there's my 6 at the top, and then I'm just transferring all the data over. I guess I could have done this ahead of time, but I didn't, so bear with me. And it's almost there. All right, so that's my A matrix. I just transferred everything that I had in my notes over, or in my what I came up with my my equations, and now I just got to make sure I transfer these. So this is my X matrix, and these are going to be, I need to make sure they're written properly or in the right order, otherwise you can confuse which, we're going to get different answers for the wrong, or the answers for the wrong variables is basically what's going to be happening. Whoops, not tab, enter. So make sure that's the same, and then my answer, my Y matrix, is going to be 0, 0, 0, 250, 0, 0. So using matrices, now I can just find my inverse. And I'm going to do a 6 by 6. So 1, 2, 3, 4, 5, 6. And I'm just going to equals inverse of this. And remember, even if I type it in, I have to Control-Shift-Enter, and it plugs in my inverse. I'm going to multiply that by my Y matrix. I'm just going to say that that equals that. Oops. Drag that one down. And then my X, my solutions for X, are going to be, whoops, I'm going to select all of them. The multiplication of those two matrices, right? And again, Control-Shift-Enter, and it plugs in my values. So if I write out my X again, and I say these are my variables that they correspond to, I'm also going to change this into numbers and get rid of a couple decimal places. So what I see right off the bat is that my reaction, I've solved for my reaction forces, so my RBY and my RAY, and I've solved for my internal forces. So FAB is 67 kilonewtons in tension because I assume tension. FBC is 211 in compression, and FAC is 83 kilonewtons in compression. What I'm going to do, what I can do really quickly though, is this came out to my RAY is 50, my RBY is 200, and a quick check that we can already say that this solution kind of makes sense is that my RBX is 0, right? So if I've set everything up and everything, there's no horizontal forces in this system, right? So there's no way that can be, RBX can be anything but 0. I also note that RBY is much closer to the load than RAY is. So therefore the RBY being 200 and RAY being 50 kind of makes sense as well. So what I can do, I can also go back with this one. It's nice and easy to check. I've got some notes here. Instead, I just left it in Excel. I can just go back and check. So if I can use the equations of equilibrium in this case to solve for my RBY and my RAY. That should be RAY. And I get the same answers. Now we could go through and we could do the method of sections or the method of joints to go through and check each of those values for the internal forces. But given that my reaction forces make sense, and there's most likely not an error in here, then we will have we probably have the right answer. So you can do a couple of logic checks. So with the resultant forces or the reaction forces, the RBX equaling 0. But the nice part about this now is I can change pretty much whatever I want. As long as I can change the dimensions of everything by changing these values here, inputting different angles and changing the values of the angles, and I can actually create an Excel spreadsheet to do that. I can make a variable for the angles, and I can change the angles, therefore changing the length. Or I can change the input. So if, let's say I wanted to change the value of the external load from 250, I'm going to cut that in half. then this will automatically solve my internal forces. I could also change it to a horizontal force, right? So, well, that would have to be changing my matrix, right? So if I wanted this to be a horizontal force, let me just see here. I would have to go back. Right now it's in the equation 5 as my answer. If I want it to be a horizontal force, I can say, if it's going to the right, I can say that there's a 250 kilonewton force to the right by putting it into my sum of the forces in the x for that joint, right? So that gives that. That's how I would do that. I can get rid of that, and I can say that it changes everything in the matrices. So all I've done now is I've changed it to because that's equation 5, I've changed it to a 250 kilonewton in the going to the left. So therefore my forces are in line. Anyway, so you can play around with the matrix and you can change the answer, or you can change the system. I could even put loading conditions on any of these joints. Basically, these are the 6 joints in either of the directions. So this would be x, y, x, whoops, x, y, x. Whoop. So you can see how powerful this would be. So this would be joint A, B, or A, C, B. As long as you keep them straight of what you're doing, you can make this a very powerful tool. Yeah, and that's pretty much how to go through a truss. I left a lot of this blank. You can fill it in with the notes and look in the Excel and watch the recording. But that's basically all I wanted to go through today. Have a good one, and I will talk to you later.